we're going to talk more about water matrix sampling. So today we're going to cover river water and also a little bit about groundwater and marine water sampling if we have time. Um, the analysis per se, it's more or less the same. Uh, as usual, the important parameters from the physical characteristic, chemical, as also biological parameters, they might be part of the analysis. Now, the way we collect these samples may be different. I mean, of course, the location and also the nature of how we should collect these samples is very much depending on what exactly that we want to know from the sample. So before I even go into the details, uh, let me remind you that sampling of water is very much dependent on what kind of pollutants inside the water sample. I think pollutant may not be the right word because, in fact, one of the important parameters that we would determine from water samples are pH, for example. They're not considered as pollutant, but we determine them all the time. And the other one, most importantly, dissolved oxygen, because majority of the pollution comes when there is not enough oxygen in the water. So regardless lah, I mean, whether it's river water or lake water or maybe marine water, dissolved oxygen is the main parameter lah to measure the health of a surface water. But what about groundwater? Is it's already underground? Does it have access to oxygen? So of course, the dissolved oxygen may not be as high as the surface water. However, they are not considered as polluted. So you have to understand, yeah, what water samples that you want to collect and their nature, because they may not be the same. So with that, I will show you the content lah, of today's lecture. So we're going to go through 5 important sections. Well, I think number 5 may not be as much. I just mentioned it through because pre-treatment and extraction, technically they are part of the lab work lah. So that is why we won't going to cover as much lah. I just mentioned what are the examples. So what will be covered mainly are part 1 until part 4. Yeah. So before I go to part 1, these are the regulations lah that we will use in Malaysia only. So DOE, Department of Environment, has already come up with a classification. So these are the so-called parameters that will be determined to calculate water quality index. Now, water quality index is a number or it's a guideline or a standard that people use to determine how healthy a water is. So you can see class 1 until class 4. Give me a second. Let me activate. Okay. So as you can see here, they are based on different classes between class 1 until class 5. So class 1 is the highest standard and they are of many usage. So based on these different classes, they have described the suitability of this water for users. So sometimes for drinking purpose, for agriculture, for recreation, usually from class 3 or below, or class 3 or above, I would say. Class 3 until class 5, they are said to be polluted. Okay, so with different level of pollution, they will have different usage. I believe the last one, class 5, are those that cannot be used at all and have to be treated, probably. So you can see that we don't actually determine all the water parameters, and it's only just a selected ones. Like for example, ammoniacal nitrogen. So they determine how much of ammonia in river water, the dissolved one. And then the next one, biochemical oxygen demand, as well as chemical oxygen demand. Now these two look similar and sounded similar, but they are not exactly the same. Because biochemical oxygen demand, you can say they measure how much of organic matter in the water. because this measures how much of oxygen is used to fully degrade organic matter. Okay, so what about chemical oxygen demand? Now, this one measures how much of oxygen is used to degrade everything, including organic matter, as well as inorganic matter. Organic plus inorganic, everything is here. So you can see how much importance we look at the oxygen content in the water, because the third one also have a lot to do with oxygen. They measure directly how much of oxygen in the water, because why? The health of a river is very much dependent on how much of aquatic life it can sustain. So of course, like aquatic life, mostly they survive with oxygen. So dissolved oxygen must be high enough so that the fishes, the aquatic organism, the insects, and also microorganisms can survive there. Because if they don't have enough oxygen, that is where you have more ammoniacal nitrogen. So a lot of people don't know ammoniacal nitrogen actually comes from the lack of oxygen. Actually, it's not just ammonia. Sometimes a lot more nasty, smelly gases. So ammonia, I'm sure you know how it smells like, huh? It's just like urine. Yeah. The other one more gas that you may come up if you don't have enough oxygen is hydrogen sulfide, like the rotten egg smell, and a few more lah. So all these are toxic and can kill aquatic life, you can say, almost instantly. Yeah. Okay, the other one is pH, because pH also may influence how much of pollutants that can be released, mobile, and are available for life form. So low pH usually a bad news lah, automatically, and low pH also is indicative of some very high uh, micro organism activity in the water. Usually the bad ones lah, if it's acidic. Yeah. And also if it's acidic, you will see more heavy metals in the water. Yeah. What about suspended solid? Now, this one may not be as beautiful like the murky water of our major rivers in Klang Valley. But the other thing that we need to know is that the more suspended solid, the more pollutants it can carry. So having high suspended solid not only looks bad, but it's also equally bad in terms of the impact to our health. I'm sure you don't want to drink a murky water lah. Everybody wants to drink clear water, right? Because that is true. Murky water usually brings a lot of problem. Yeah. And from all six of these parameters, they calculate water quality index. So this is how. Now, if you have time, spend some time and visit this site from DOE. So these are the so-called water quality standards that Malaysia has been using. And actually, inside this document, there are more, not just these six parameters. Yeah, there are more, including heavy metals plus a lot of other pollutants. So you might want to have a look. Frankly speaking, this standard also did not cover all the pollutants that we have, because pollutants, they're all emerging. From time to time, they might be like new pollutants coming up because these pollutants are man-made. Yeah. So yeah, there are some weakness lah in this standard because they not yet covered everything. Okay, so those are the standard. Now we move on to the design of water sampling. I know on our first lesson we learned about how do we design. So this looks like very much the same as what we learned in the first chapter. How do we design a program that we want to monitor the water sample? So there are four types. Rapid assessment. That means if there is if there's an immediate incident of a pollution, of course, DOE usually will going to go to the site and then do some monitoring, the scan through where at the source, how heavy is the pollution happen. So that is what rapid assessment is about. When there's incidents, you go there and you collect water sample. The other one is establishing baseline. So when there is no incidence of pollutants, but you just before you go into a monitoring program, you want to know the existing level of parameters, water quality parameters there. Doesn't mean that there is a pollution, but you just want to know, okay, that is a baseline level, the natural level of water quality right there. Yeah. And then perhaps we might proceed to a long-term monitoring program, just like what DOE has been doing. Yeah, there has been a steady long-term monitoring program to assess uh, from time to time the water quality level for river in Malaysia. So this one involve an extensive network of system stations that are put permanently into a certain location, strategic location in a river, just to monitor the changes of water quality. Because maklumlah, from time to time, Malaysian population has been increasing for the past 20 years. Maybe around this time it has stagnant, but with increasing population, the river water also may come down. So that is why the monitoring system is there. And also problem assessment. This one looks very similar to the earlier ones, but this one, when there is an immediate incident, yeah, then there will be one. So what is rapid assessment? uh, Simply wants to know the water quality. Is it good or bad? So may not represent the actual condition of the water source. So this so-called rapid assessment is only true at the time where the water quality is collected. So it's very time specific and location specific. So this one is used to create awareness. So it may not have like an incidence at the time, but this one is like suka-suka. You just want to create awareness, and it's often inexpensive because the time and also the number of samples you collected is only on that time only. You're not going to collect long term a lot of samples from a long term monitoring program. So I would say this rapid assessment is very much like what we usually do like in the field trip. We just want to go to the site. I mean, show students how water samples are collected. At the same time, uh, give them awareness how river water is being monitored. And there are a lot of these programs conducted by NGO per se. If not mistaken, there's one very prominent one in Klang Valley. If not mistaken, okay, I remember the short, I mean the acronym GEC, Global Environmental Group. If not mistaken, GEC. I forgot what is the C meaning, but yeah, that is an NGO located in Klang Valley. So next one is establishing a baseline. So this one undertaken prior to establish a long-term monitoring program. So before a long-term monitoring program started, this one is needed to establish the baseline lah. So this one only is established only at the time lah, at the time where it is collected, very similar to the rapid assessment. Whereas the long-term monitoring program, you do it all the time over a long stretch of time to monitor the changes at a strategic location. And problem assessment, when there is a pollution happens, so this one comes in very much the same like rapid assessment, but this one have an incident. Example like in where is it? Sungai Kim Kim, very famous last time. Suddenly, student gets sick, and then they discovered many barrels. So there you go, DOE. They come down and collect water sample. So that is part of the rapid assessment. Sorry, problem assessment. Okay, now so a little bit of things that we need to consider lah before we go and collect water samples. We need to come up with a few strategies because, like I said, it depends on what pollutants that we are dealing, and also how do they change over time. Now, these are the examples of water characteristics that would define the quality of a water. So if we look at water quality index that Malaysia has been using, we only select a few parameters from here. However, if you go back after this and you compare the water quality index from other country, they may have other characteristics. And I don't think we need to go too far away overseas. Just compare lah, yeah. Because in Malaysia, if you're looking at river water, there are several agencies that governs it, mainly DOE lah. But when we touches about groundwater, maybe DOE involved a little bit, but that's under the jurisdiction of Jabatan Mineral and Galian Malaysia, JMGS. So it's a different department altogether. And what do they look at? They probably don't look at dissolved oxygen that much, but they probably look at other things like dissolved mineral, heavy metals, and so on. So that is why when we talk about water characteristics, depends on what water you collect. And that is why different characteristics also might be involved to define its quality. But one thing that is very glaring is that in Malaysia, we probably should look more on the biological parameters, because I think this is the one that really gives sickness lah, if water has been used. Surprisingly, in Malaysia, we don't have biological parameters like total coliform, how much of bacteria that exists in surface water. But one more thing that you need to remember, okay, Malaysia is a bit complicated lah, yeah, because when it comes to water for drinking purpose, for human consumption, potable water, the the Ministry of Health, KKM, okay, KKM comes in. Very strange, yeah. When we talk about water, so many agencies comes in, because when we talk about the human health for potable use, KKM have another guideline, okay, in which one of the most important difference lah, yeah, apart from all the parameters measured, they have chlorine level. You see, it's not even here at all, yeah, because we are comparing environmental water. I mean, the one in river, lake, or some odds, and so on. But we talk about pipe water, tap water, there will be chlorine level, and there are also a few biological parameters. So only for potable water, KKM looks at it. DOE, if it's environment, is okay. Yeah, because there is a truth also lah. Because why? Naturally occurring water in river, of course lah, we're going to have bacteria. It's just a matter of how much. The more polluted a water, maybe polluted with more nutrient, the more microbes inside that river water. Although that is also a measure of water quality, but it's unavoidable. When you have more nutrient in water, not just water, like in soil also, you're going to have more microorganisms. It's natural. So probably that is the reason why for environmental water quality, bacteria is not look at it that much, because maybe it does not represent as accurately the river water quality. Yeah, because why? In Malaysia, nobody drinks directly from river, kan? Well, hopefully that is the case lah. Okay, so another one more thing that you need to know is that what about the changes, the variability? Now, just like air sampling that we learned last week, water sample also change in quality all the time. And they also change with climate. So as you can see right here, this so-called heavy metal levels. Now this one is gathered from USGS, US Geology Survey. They measure the groundwater level. So this is from groundwater. The changes over a long period of time, over 2 months. So how come they change like that? Now apparently this one is from a ore creek. You can say it's not really a groundwater, it's more of a surface water, but many surface water actually sourced from groundwater as well, so they are connected. The levels of heavy metal, zinc, manganese, and also cadmium and arsenic. So these are the ones that usually available in groundwater when there is a mining activity, because they come from the minerals itself, and it changes over time. Now, why is that? Because over these 2 months, there might be some patterns in terms of rain. Okay, that's number one, pattern of rain. I mean climate lah, factor. The other one is natural factor related to the physiology of microorganism. So when microorganism, they might be active in a certain time, like for example, maybe daytime when they have sunlight. Some of the organisms, they rely on photosynthesis, so that's why there are some levels of heavy metals that are higher or lower. Yeah. Now, not only that, when you look at the diagram down here, also zinc load, how much of zinc in the river water, you can see that it also changes from location downstream and also upstream. Because if the location or the source of pollution happens to be in uh, downstream, the closer you move to downstream, the higher the pollution, and vice versa. But there is another explanation to it. Because why? When you go down into the river, we might disturb the riverbed. So the sediment comes out, floats in the river water, and they flow downstream. So maybe downstream have higher heavy metals is because there are disturbance by the sampler itself. And this is also one more thing that we need to pay attention lah before we go and collect water sample. When there is a disturbance, it does not represent the original state of the river water. It becomes polluted because we, the sampler, disturb the water. Does not represent the water, the river water. Okay, so invalid lah. So you have to remember, no, when we collect water samples, we have to know where should we start and where should we end. Yeah. After this, I'm going to elaborate further lah, yeah, about this one. So another thing that we need to look at is the strategies and also what kind of analysis that we are going to conduct. Is just like the one that we look at just now, the assessment. What kind of assessment? So based on these samples that you have or the standards and also different analysis, temporal or spatial, they might require different time that you have in order to collect and analyze the sample. So some may have like longer time frame, like chronic standards. If it is acute standard, um, it has to be measured immediately, as you can see right there. Whereas some other analysis like temporal, that means time-based analysis, like usually this one are part of the monitoring program based on different time, or maybe spatial analysis. You want to see the migration of pollutants from its source. Maybe you want to sample 24 hours to see how much they migrate because water flows quite fast, not like soil. Yeah. And also comparison of those temporal or spatial, you want to compare the difference in terms of levels of pollutants over a certain period of time or over a certain range or distance from the source. I mean, you may want to analyze more than one, but like I said, it all depends on how I mean what are the purpose that you want to conduct this monitoring program. Yeah. So it's also very much dependent on how much time that you have from collection to analysis. Again, if it's too long, it may not be valid. Yeah, it may not be valid. And then, like I said to you just now, the sequence of sampling, because when we go into the site and collect samples, we might cause a little bit of disturbance. So, like I said, collect water first and then the sediment. Because when you touch the sediment, it will comes out and disturb the water quality. Yeah, we try to avoid cross contamination, yeah. And then next one, river may not be all very shallow. Some of them very deep. Yeah. So usually the surface water will going to have more oxygen and less sediment. So if that is the case, kan, it is considered like usually the surface water, they are relatively of higher quality. So you collect that one first. Then only you collect in the deeper water. I mean, very simple. Deeper strata of a river usually will going to contain heavier content. I mean, heavier uh, components that includes sediment. So when river flows, the current will carry a little bit of sediment, but they may not float as high. They may just going to hover around the riverbed. So when you collect deeper water, you perhaps going to get more sediment, less oxygen. But if you pull it up, it will bring a little bit of sediment. So again, cross contamination, even within different strata inside a river. And then, of course, like I told you just now, sampling at shallow stream, and then you go up to you go to the upstream. You start from downstream first, and then go upstream. Because why? When river water is flowing against you, they flow against you. Whatever that you collect at the time, whatever the sedimentation that happens, all travel past behind you already. So when you move up, technically there are no disturbance, even though you're already inside the river. So always remember, face the current, move from downstream to upstream. Yeah. So that is the usual sequence. And then there's another one. If you want to look at more than one analyte or more than one pollutants, you might want to start off with the one that is the least, the most mobile, I would say, or the least controllable analyte. So in this case, gas, usually they are considered very, very mobile. And if there's a need to analyze volatile analyte like VOC or SVOC, oh, by the way, VOC stands for volatile organic carbon. It's volatile. Semi-volatile organic carbon, they are less volatile, but they still is with different temperature. And there might be another one more in inorganic component, which is also volatile, which is ammonia. Yeah, let's not forget in water quality index, we also need to analyze ammonia. So usually those are the ones that we need to pay more attention. We sample those ones first and treat them first. Because why? Once you collected those samples, they will start volatilize already. The levels of this volatile analyte will start changing the moment we go in there. So if you don't immediately collect them and treat them properly, they might be released and you might have underestimation of this compound. Now the next one is total metal and also dissolved metal. So you can collect these two. And the preservation is usually acid. And then finally, microbiological samples and inorganic non-metals. So these are the sequence that we usually follow. Yeah, where we want to collect a water sample. And very important because we cannot afford to collect water samples that much because where do you store it? And also, do you even need to have that much of water? But if you ask me, I would prefer the more the better, as long as it represent the location, yeah, the river water, for example. Um, because a small sample size usually is disastrous lah. In terms of the variation, because river they flow all the time. You cannot just collect there. You have to collect probably along the river. You probably don't mix them together, but more sample size so that you know the migration of pollution and not just right there at that time. It's you have better knowledge on how pollution happens there. Um, but then how much of water that you need in order to have a reliable data. So later on, we're going to talk about how do we ensure a reliable sampling in order to have like a quality data from a QC, QA, and a QC program. So how much do we need? Uh, so I can see, as you can see right here, for trace metals, maybe 1 ml is enough per sampling point. Whereas for total organics, you might need a little bit more, 1 liter. Now, reason because organics, if it is a pollutant, just like VOC and SVOC, they are not expected to dissolve too well in water. So you can expect a very low amount in your water sample. That is why having more is always a good idea. So that if you don't have enough, then you extract from a higher volume so that you have enough organic analytes to be able to be detected, to be detected by instruments that you have inside the lab. Not all instruments they are that sensitive, so you may need a bit more of the sample, And then lastly, 20 to 40 liters for an effluent of acute toxicity test. So this one you may have a bit more requirement from the test itself. So you need to know like what methods that you use. But usually that is the general idea of how much water that you have. So based on this volume, you can expect lah the container to be used can be as small as a urine bottle. Yeah, when you go for medical checkup, you have a small bottle, right? As small as that, um, or maybe as big as a what do you call it? A carboy, you call it. It's like a water tank, very big. You can hand carry. The capacity of those carboy are usually 20 to 40 liters. You can get as much as that. Whether or not you need that much depends lah. I mean, on your sample, on the purpose of your sampling. Yeah. Okay. So we are moving to water sampling, preservation, and storage. Now, before I continue, there will be a lot of chemistry coming in. Um, so I need you to start off fresh lah. Just want to ask all of you, are you all still fresh enough to continue? Because there are many chemistry things coming. Um, if you want a 5 minute break, I can give you a 5 minute break so that we have a fresher mind to go through this. Do you think you can continue or you need a 5 minute break? Continue, okay. Can
Yeah, can continue.
okay. Have a fresh mind because in water sampling, you can say this is probably very important lah. And you will expect question from this part onwards. Yeah, many. Now the reason why I warn you here is because when we talk about chemistry, kan, and you don't understand, usually your mind shut down. So I don't want that to happen, lah. Yeah. Okay. But as a refresher, lah, the equipments I'm going to start first. Yeah. So what are the equipments that we use to collect water sample? As you can see right there. Now, this one is called pond sampler or a grab sampler. It is a pole, a very long pole. Attached with it is this cup, a small cup that is used to scoop surface water directly from river, the bank, I mean from the side of a river, or maybe on the surface of a lake. Now, this one can be used, but rarely used. Um, because it does not actually measure water from a deeper strata. So you can say this one is for shallow river, you might say. Not many people are using it. Oh, by the way, there are videos that you can watch right here. But let's continue. Let me finish all the slides because I'm worried that I don't have enough time to finish all my lecture. So once I finish all the lecture, then we might go through the video. Yeah. Now, whereas the other two, the B and the C sampler, they have a different name. We call it weighted bottle sampler. So this one is a stainless steel uh, sampler or a device lah. You call it stainless steel. It can be attached to a reagent bottle. So reagent bottle, most of the time they're glass and heavy enough as well. So they're attached to here, and they can be tied with a rope where you can lower down either from above of a an overpass or a bridge, or maybe from a boat. You can lower it down to a certain depth, and then with a trigger, you can release the cork and let the water flows in. So once the water finish flows in, and there is a mechanism that you can lock it up, and then you release back the cork, and then it will shut down. So this reagent bottle filled with water samples, you can pull it up and then you can pour it inside your maybe sampler bottle or whatnot. There is another one more water sampler which is called Van Dorn sampler. Uh, it is very similar to camera bottle, As you can see right there. Now, Van Dorn sampler, uh, they are a tube. They are a tube, and it is operated horizontally. So the tube is placed horizontally, just like this one lah, but only horizontally, in which each side they can they can set up and then release the opening to allow water to flows in. It's just like the camera bottle right here. Only camera bottle is vertically lowered. So this one is lowered vertically, whereas the other one is horizontally. Okay. Um, I think DOE use a lot of Van Dorn sampler. There are pictures that I saw from its website, and they use primarily Van Dorn sampler lah. Yeah. Now, one very logical thing is that when you have Van Dorn sampler, I mean, placed horizontally, you can use that even with a very shallow river water. You can lower down. Very shallow, no problem, because it's horizontally. Whereas if you put this camera bottle, right, it is vertical. And if it's very, very shallow, you cannot operate using this one. Okay. And usually camera bottle, they are used in a very deep river, lake, or maybe marine water sampling. So which one is more suitable, I cannot say, but usually Van Dorn sampler lah, they are easier to use here. Okay. So as you can see right there, pond sampler, the suitability near the shore or the river bank, they cannot collect deep water sample. Now camera bottle, they will have some more components lah that might have Teflon, stainless steel tube that you can attach. But overall, these camera bottle and Van Dorn sampler, as well as a weighted bottle sampler, they can be lowered down using a rope tied to it. So you can say the depth where they can operate is limitless, yeah, depending on how deep you want to collect the water sample. But there are differences lah between camera and Van Dorn sampler, in which one is lowered down vertically, that is camera, and the other one is horizontally, that is Van Dorn. And when you start collecting water sample, one of these might going to collect a little bit of sediment as well. And that is Van Dorn sampler, because they're horizontal. They can be lowered down so low that it can be like the same level of the riverbed. So if one of the purpose is to collect water sediment as well, then Van Dorn sampler is more suitable. Okay. So basically, those are the examples lah. Hopefully, on next Thursday, we can get a glimpse lah on how this sample looks like during our academic visit lah to Shuriken later on. Okay. Now the fun part has passed because I did not show you the video. I'm supposed to show you the video of how this one is operated, but if time permits, I'll show you lah. This one can be said is the important one. How do we preserve water sample? As we know, water sample changes all the time, because inside of your water sample, you can expect some microorganism inside. How do they change? We don't know, because it depends on what kind of microbes inside. If it's a bacteria, maybe it would turn the water more acidic and whatnot. If it's a fungus or maybe mold, they may change differently. Hence, the first part of this strategy, or the way we preserve water sample, is always cool it down. No matter what analyte that you want to do, you always refrigerate it. Cool it down to between 2 to 4 degrees. I won't say 6 lah. 6 is still not low enough. It's 4. We usually cool it between 2 to 4 degrees Celsius, because at this temperature, bacteria can be said all relaxed, all inactivated, and you can buy time lah, because once they active, they release all sorts of things kan, their organic acid and whatnot. So at this temperature, okay lah, they will last for a while, enough for you to travel back. And You also need to have dark bottle, especially those that you want to analyze is were very light sensitive, like um, iron, for example, or maybe chromium. Now, these are the heavy metals that once you have light exposed to them, they may have photo oxidation. So if you want to look at different oxidation states, it may not be that accurate, yeah. And of course, light also may induce photo oxidation or photolysis of organic compound. So that is why it needs to be collected in dark bottle. Now, there are a lot of reactions that might changes the quality of your water, and they are here. So microbial degradation, I already mentioned just now. Chemical reactions are quite likely, especially when you expose or you uh, restrict airflow into it. Because when you collect water sample, before you collected it, it's always exposed to the environment, the air, for example. It is oxidized. You collect your water sample in oxic environment. But when you put it inside the bottle, you will screw you will screw cap it. You kept it airtight some more, kan? Nobody collect water sample by opening it, because you collect and then after that you come back all tumpah. It's impossible. You must screw cap it tightly so that it doesn't spill over. Now, you have to remember, once you start screw capped it, that is a moment you are changing the water quality in terms of oxygen. So remember just now we want to determine dissolved oxygen, kan? You screw cap it, then oxygen comes down straight away. So that is part of the chemical reactions that we might induce during sampling itself. So when we collected samples, we are also changing the chemical properties of the water. And there's a possibility of volatilization, because why? Because some analytes, they can volatilize just like what I show you, VOC, SVOC, and also ammonia. And this is a natural process, adsorption and absorption. Now, the difference between these two, adsorption is the analyte will be located on the surface of a solid. Adsorption happens on the surface only. Whereas absorption is, it goes into the solid. This is just like sponge lah. You absorb water, so this is why it goes into the sponge. Adsorb, it landed just outside of the solid. But all in all, why do we matter? Because why? Your container, for example, your glassware, whatever that you put inside that container, adsorption happens straight away naturally. That is a natural process inside the wall of your container. Adsorption straight away. Absorption depends, because some of the analyte, uh, say uh, organic organic pollutants, for example, organic analytes, they might interact with plastic, because plastic also comes from the same thing, organic component as well. So they might have absorption. That is one example. There are many more, but this is what I can think of. Whereas diffusion, now diffusion may happens when you have a source of pollutants, like for example, a sediment. If you accidentally collect sediment inside a water sample, earlier I told you that sediments may have a lot more content of some analytes or contaminants. So once you collected, they may start diffuse within that container. And surely that does not represent the water sample that you collected from a site, from a river, for example. Yeah, so that might happen. Photo reactions, I think I told you just now from the dark bottle, so I'll skip. Yeah. So a long story. There are many ways that we can change, that a water sample can change. So these are the reactions lah. You see, there are many points here. They are very suitable for essay question, but you can be relieved lah, because why? We don't have final exam. and quiz is not suitable for final exam. But still, I still can ask you a lot of questions, can, on how water samples may change from all these reactions. So these are the examples. You don't have to memorize, but make sure you're familiar, lah, yeah? At least you can explain logically. All right. Now, what should we do in order to address this? So while we cannot avoid this reaction from happening, but at least we can minimize the changes. So how do we minimize? Apart from refrigeration, we can preserve it. Preserve it by using suitable chemical. Either we use acid, or we use base, or we even use biocide. Biocide is can be said as a preservative lah, to kill germs, bacteria, microbes inside the water so that they stop messing with your water parameter. Yeah. And then of course, proper container, because some container may not be compatible with a few analytes. So you have to know when to use glass, when to use plastic. You may even want to consider when you want to use a cap one or a septum one. Now, cap is fully covered with hard plastic. Septum is in the middle of the cap. You have a soft membrane where a needle can be poked through. It's just like your vaccine bottle on the top. You can poke through the needle and you inject kan, something like that lah. And also amber bottle, because if you have things that are photosensitive, amber bottle lah is what you need. Okay, a lot of story, but what's next is even going to be more challenging lah. But before that lah, yeah, how do we refrigerate the water sample? Of course, fridge is too big. You cannot bring it. Although you can technically bring a uh, a lorry equipped with refrigeration. You can do it, but I don't see so far DOE doing that. So it's not economical lah. Number one, it can be done, but not economical. Because refrigeration can be done as easy as using an ice box lah. Ice box is good enough, because why? You collect sample, you immediately return to the lab. That is okay. No need for the ice lorry lah. No need. Um, so how do we maintain 2 to 4 degrees Celsius? There is a secret. We will use water ice or wet ice, in which what you need is packs of ice where you can buy easily from a convenience store. Okay, you can buy 2 packs, and then you pour it inside the ice box, fill with your water sample. Okay, inside, of course lah, bag properly and inside the reagent bottle. Then you start pouring water until the bottle fully immersed under the water level. Now, when this happens, kan, water helps cool down alongside with the ice, because water, when the bottle is inundated with water, it increases the contact between the ice and also the bottle. So the cooling effect is much efficient than without water. So we purposely add water lah, but not until it fills out. Just enough lah, yeah, just enough for them to have enough contact with the bottle. Now there are a few things that you might ask me. Where do you need to add glycol-based ice pack? I've tried it before. Glycol can cool down the ice box, but not as good as ice. I mean the pure ice, wet ice that we have here. They can cool down, but not cool enough. Okay, there's another option. Can you use dry ice? Now, dry ice we don't encourage for 2 reasons. Although here they say they don't recommend because they might over ice the sample. Water sample might be frozen and cause breaking, because when water turns to ice, they will expand. So over expansion, they will break the plastic. They also even break the glass, and you don't want that to happen, like that. And some more also, when you have a frozen water sample, it might change also the characteristic of your water. So that's why we don't even want to ice the sample. But of course lah, there's one more thing. It's due to safety, because dry ice is made of carbon dioxide. And when you put this dry ice inside a container, they will slowly release carbon dioxide. So imagine like the entire car full with carbon dioxide. You go inside there, you may pass out inside the car. And of course lah, even if you don't pass out, slowly you feel sleepy because you have less oxygen, more carbon dioxide. Yeah. So there's also another safety aspect lah to why we don't use dry ice. Yeah? Okay, so this is the beginning of a lot of things that you thought you want to memorize, but I think you just focus on the general part. Yeah. And this table summarize lah the general things that you need to know. How do you preserve your sample based on different analytes, and also the changes that might happen lah based on these different analytes as well. So to begin with, the easier ones, also perhaps the most famous one, metals. Some even say heavy metals. Okay. Now, if you want to look at the metals inside water sample, you will need to make sure that they are uh, aqueous or ionized all the time. And there's only one way we can do that, which is by adding nitric acid. So how much of acid that we need to add depends on the concentration of nitric acid. And let's not forget, we are not trying to change the concentration of other analyte as well, which is why usually concentrated nitric acid is used. How much they added? Just 1 or 2 drops. 1 or 2 drops of nitric acid added to the sample bottle, usually plastic lah, usually. And that is enough to lower down the pH into less than 2. It has to be acidified. Because once it is acidified, this metal will not precipitate, they will not form sediment, they will dissolve in the water. So what you measure is accurate. Okay, you might ask me why you use plastic bottle. Why do we even not using glass bottle? We thought that glass is very clean, may not interact. Plastic looks like soft or somewhat. But there's a thing that we need to remember, yeah, when we have metals and also acidified condition, acidified metal solution, they don't interact as well as plastic because plastic comes from organic oil-based material, so they don't interact that much. So in terms of interactions and also cross-contamination, they are said to be quite low lah. Uh, so that is why. And one more reason, plastic light is very light. Glass kan, is very heavy and they break very easily. So that's why plastic is very much preferred lah, yeah. Than glass bottle. Okay. Okay, next one, phthalate ester. So this one is the organic compounds that may escape due to volatilization sometimes, or they might diffuse into the plastic because this one is one type of organic components and they are very volatile, so they might diffuse into plastic. Now, if that happens, if that is a possibility, you might want to get a specialized container. So this specialized container, inside the wall of the container, they are lined with Teflon. So Teflon is a membrane very similar to your non-stick cookware. They don't stick. Nothing can stick there. Or in this case, they will minimize the absorption of this organic phthalic ester into the bottle, and they keep it inside the water sample. Yeah. In fact, most of the research involving detection of volatile organic matter, we always use a container that is lined with Teflon. I know Teflon container is very, very expensive. Sometimes it can be up to like hundreds or thousands of ringgit. But trust me, no organic matter can stick on the wall and you will get an accurate result coming from here. Yeah. But if oil is what you have and you don't have too much money, a glass bottle also can be used lah. But there's still some risk lah. Oil might stick to the wall of the glass, so there are a lot of things that you need to uh, pay attention lah. But if money is not really a problem, then Teflon. I would recommend Teflon. Okay, the same with VOC. How do we prevent volatilization? We avoid headspace. That means the the container is filled with all of them, water sample, with no air at all, because once you leave a headspace, that means air, no matter how small, there is a possibility that a small amount of your VOC might be volatilized on top of it. It's the same with ammonia. But ammonia is different a little bit simply because it may react with sulfuric acid. So when you have sulfuric acid added inside there, you acidify the water, and this ammonia will be attached to sulfuric acid forming ammonium sulfate. So ammonium sulfate, they no longer release the ammonia and they dissolve in water as ammonium sulfate. So you see, there are two ways. There are two ways you can acidify water, but they also use different kind of acid. So you also need to know lah which one is more suitable for you. Okay, sulfide also may be volatilized because when you have bacteria, they may be volatilized as hydrogen sulfide. So you add all these things as a preservative. Cyanide also may be volatilized. This one is even more dangerous because it may kill you. So adding ammonium, sorry, not ammonium, sodium hydroxide, you alkaline it. You see, all this while we learn about acidification, but suddenly there are a few analytes that you need to put alkalines, so sodium hydroxide. It depends lah, very much. It depends on what you want to analyze and the nature. Because why? These two, when you have high pH, they will be immobilized under high pH. Okay, so remember, some analytes, they might be immobilized at high temperature, sorry, high pH or high or low pH. They're very different in their nature. Um, so let's see about organic matter in drinking water. So it might interact with chlorine already inside the drinking water. So you might want to have this anti-chlorine. So for those who have aquarium at house, this is actually your anti-chlorine. Sodium persulfate. Wait, is it persulfate or hyposulfate? Persulfate, yeah, persulfate. To remove free chlorine. So this one will interact with chlorine and they will eliminate the chlorine. So your organic matter will not change lah, or will not be oxidized by chlorine. So chlorine, when they're inside the water, they will break this organic matter. Of course lah, it will break it and you have lower content of organic matter. So PAH is not so volatile, but it's said to be semi-volatile. But the concern here is not just volatility, but also its photolysis due to light. So light, when it shines into water, it might break a few. So that's why amber glass bottle is needed. And when you have organic matter also, it might be exposed to biodegradation. That means the bacteria might start degraded. So in this case, usually preservative is added. Mercury chloride. Well, I think there are better options, not mercury chloride. There are a lot of other options that you can do here. Uh, I think maybe because you want to analyze organic matter, that's why the antibiotics are not used. So they use a metal base lah. Mercury kills them, yeah. And then if you have totophenolics and you want to stop bacterial degradation, sulfuric acid also can be done. So students, if you want to prepare you want to prepare for your quiz or whatnot, maybe this is enough lah, I would say, because this table encompasses various types of analyte inside water sample, the risks that may change the quality during storage, and also how do we preserve it. So this is the simplest lah, the most summarized way, the most summarized content regarding to preservation method according to Enlight. So if you want to study, okay lah, you focus on this one. But please, this is not the only information that you should get, because if you look at other slides lah, yeah, like here, there are many more. Now this one also touches about containers, and also some other ways of preservation. And this one also, you may have preservative with different kind of organic pollutants. In a minute, I will come back to this. So you want to study a bit more like what? So please don't limit yourself to that table earlier. I know for exam, that is a one. But in reality, you need to study a lot more. There are a lot more, yeah. You don't need to memorize, but you just focus on the general parts. Yeah, like for example, heavy metals, acidified it, nitric acid. Yeah. Organic compound, you use glass bottle, and you're going to use amber glass bottle, which is why we are here talking about the containers. So you have various types of containers. Like I said, this is septum, yeah. And why do we even use this one is because, especially this one, yeah, the one with amber bottle, because this is vial, and they are usually filled with water samples that we want to analyze the organic content, pesticide, for example, because pesticide they degrade very fast with very strong sunlight. So when they are put inside here, this vial is put directly in maybe HPLC, maybe GCMS, in which the machine there will have an auto sampler with a needle. They directly poke inside here and then they analyze straight away. And why this is so? Because why? The moment you open gun, it will start releasing the organic content. So usually we don't open it at all. We just inject, put a syringe inside here, not syringe, a needle inside here, in which the sampler will draw water sample directly into the analyzer and straight away we analyze, so that we minimize cross contamination or loss of analyte. Okay. So of course lah, the other one maybe for analyzing total organic carbon in dissolved organic carbon or whatnot. But the popular ones lah, let's start with the popular ones are this one, the small plastic bottle. Wait, I think this one is Teflon. If you don't know how Teflon looks like, this is how. You thought it's dark color, right? Because your non-stick cookware, they are black. The membrane is black. They are actually colored. Actually, they are colored. The the original color of Teflon is actually like this, just like any other plastic. So this is polyethylene, high density polyethylene. The famous one is this one now, because why? Cheap, light, and very durable, and can be used over and over again. This one is preferred. The other two, amber glass bottle, because when we talk about glass, usually it's about organic analyte, so that's why it's usually amber. But at times, kan, this reagent bottle may be used. I mean, of course lah. Remember the what they say, weighted bottle sampler. Yeah, you need this. Either yeah, these are the reagent bottle lah. This one you have a stopper. The other one you may have like a screw cap. You have a cap. A lot of things that you can use lah. Okay, now selection of sample container. I think I have explained this one already. When do you use glass? When do you use plastic? Glass, organic pollutants, plastic, inorganic pollutants. Yeah? Headspace or no headspace? Headspace, I mean, if you don't have volatile analytes that you want to look at, if you do, then please don't allow any headspace, any air inside the container. Do you need special containers? Well, depends. If you have a very small analyte content, and that analytes might stick to the wall, then you might need a Teflon line plastic container or glass container. Now, the other side is that if you want to look at the microbes inside water sample, you might need to cover it with aluminum foil, and then the stopper is lined with this. Okay, so that is if you want to look at the biological properties of the water sample. Okay, and then aluminum foil should not be used if mercury is in the target. So if the water sample contain mercury, don't use aluminum. Why? Now mercury will interact with aluminum foil to form an amalgam. So it might cause cross contamination if that happens. Yeah? Okay, now this one I would like to go through really fast. Look at the general thing. So based on the purpose of your analysis, you are going to need to prepare it differently. Now, sometimes when we collect water samples, we either collect as it is, unfiltered, or we filtered siap-siap. We filtered before we even bring it to the lab. Because you can say that the sediment is always there inside the water, and it's not just sediment, sometimes dissolved organic carbon. If you have that in water, you cannot see it. It's just appeared jelly, I mean, it's like gel if it is concentrated enough. But if it is very low, you don't even notice. You're probably going to see water that is a bit yellowish. Okay, if it is yellowish, that is a telltale sign that you may have dissolved organic carbon. And depending on the standards, yeah, I think the water quality index that we've seen just now and their parameters related to heavy metal, we will always look at the total metal. But if you want to look at another form like complex metal, if you want to isolate complex metal, uh, why metal can be complex? Because they interact with dissolved organic carbon, they form complex. So that's why we call complex metal. And these metals are usually quite available biologically. Sometimes more, but more available than the aqueous metal, the metals that are cations, for example. Uh, if that is the thing that you want to analyze, then you need to filter. So filtering using what? Using 0.45 micron syringe filter. You can use a membrane, but usually we use syringe filter. It's very handy. You can attach to a syringe and you press it. There you go. All filtered with this one. And once this is filtered using this pore size of a syringe filter, the water sample has been removed of all the sediment, of course, as well as dissolved organic matter. So what is left there, if you have metals, they are of ionized metal. There is no complex metal. I know I explained a lot, and you might think, why do you even need to know this? Because in chemistry and environment studies, we look at this because there is difference. There are difference between ionized metal as well as complex metal. They are quite different in terms of their properties and also their availability. Yeah. So the rest is similar lah. You put it inside HDPE container, and then you acid rinse it, acidify it later. The usual thing lah, yeah. The only thing that is not covered just now is the filter lah, yeah. Some of them they need to be filtered, some of them not. But you have to look at lah what are the things that you have inside and what you need to analyze. So these are examples lah of metal or metalloid. So in this case, arsenic is metalloid, iron is metal, both of which may exist in many forms, many oxidation state. So to prevent that from happen, you have to put it directly into a amber glass. Yeah, amber HDPE bottle. Because when you have sunlight and then when they receive sunlight, they will change oxidation state. Sometimes not even photo oxidation. They might also happens photo reduction. So sunlight can mess up with a lot of your sample. And these are the ones that is highly probable in which their oxidation state might change due to different sunlight. And do you know why we look at arsenic that much? Now maybe iron not that much because iron 2 and iron 3 toxicity maybe not that much, but arsenic, for your information, there are two major forms: arsenic 3 and arsenic 5. One of these is extremely toxic. The other one is okay, tolerable. So if you want to determine the toxicity of a water that contains arsenic, most likely it is very dependent on just one species. But if your sampling technique did not preserve that ratio, we call it, the ratio between these two species, you might not get the accurate picture of the toxicity of the water sample, which is why you need to preserve inside amber bottle. Okay, a lot has been said and a lot is covered here, but I think I'm repeating a lot of things that I've mentioned earlier. So I will let you read it yourself. So these are the examples, very similar to what I've said earlier. You can read it yourself. And coming to this one, again, a lot of similarity. What are the containers that we use in order to collect the analytes on the left hand side. A lot of organic analytes that you can collect. Some of them volatile, some of them not. Some of them you don't even need to fully fill it. Some of them you have to fully fill it because they are volatilized. They are volatile analytes. So you can refer to this one. Yeah. Okay. How are you all holding up? Do you need a 5 minute break? Can we continue? I think if possible, I would like to ask for continue because now I think I probably don't have enough time, just enough for me to finish this lecture. Can we continue?
Okay, better.
Can
Can continue.
okay. So a lot have been said about that one because that is a major component. When I say longer, that is an importance for your exam and test. So pay attention lah, yeah. Okay, maximum holding time equally important, but I think the next one would be the direct lah message that I want to deliver. When you look at these different parameters, they have different maximum holding time. That means how much time can you wait and store before an analysis? Because if you pass that maximum holding time, the result may not be valid. Like I said, all these water sample, they change over time. Some change very fast, some change not so fast, very slow. And because of that, you can come up with a different time frame where you can prioritize what parameters that you need to analyze immediately and otherwise. So here you go. Let's start with the further left-hand side of this table. The parameters that you need to analyze as soon as possible. Not as soon as possible, I would say immediately. These are the pH, salinity, the chlorine, or per per chlorine. I would say maybe wait, chlorine dioxide lah. Let's call it, yeah. Carbon dioxide, iodine, ozone, dissolved oxygen, and temperature. All these things, they are gas or maybe parameters that change very quickly, temperature and pH. And we already have a solution. There is a device we have, we call multi-probe array. Multi-probe array. There's a probe that inside that probe, there are several electrodes. Electrodes that you can dip into the water and do reading straight away. No sampling at all. Just dip it in and there's a display panel where you can see pH and all of these things, some even more. Yeah. Nowadays, technology has really catches up at the advent of Industry 4.0 for your information. And some of these array don't even don't even connected using wire. They are like Wi-Fi. You can actually get this result directly from your phone nowadays. Yeah, there's a probe, you put inside water, and then your phone start logging. Your phone is now can be used as an data logger. Don't be surprised nowadays. Yeah, and there are some other samples like if the other things that you can wait, you can wait, but you have to remember also some of them they cannot wait too long. Like for example, this one. Once you sample, you only have 6 to 48 hours to conduct the experiment to finish up all these things. So as you can see right there, different parameters, different time frame lah. Yeah. And the other ones, 7 to 28 days. You may have longer time because maybe they are less volatile. They are not too affected like by the changes of bacteria inside the water. Like for example, all these things lah. But still, you cannot store your sample forever. But the best is like metals lah. Metals, they are not destructible by bacteria, which is why you can see here. The hardness actually comes from a lot of metals from the water. As long as you acidify the water, it will technically be there. Yeah, it's there forever. But why you still need to analyze in 6 months? Because after 6 months, your metals might change in terms of their phase, The phase means maybe from dissolved phase, it may change to solid phase. Some even might react with the materials of your container. If they're given long enough time, they can do it. Yeah. So you still have 6 months. But frankly speaking, this one is probably the easiest. Acidify straight away, you send to ICP, then you get the result straight away. Even faster than this one. The analysis from here. Yeah. So remember, yeah, these are the maximum holding times. Oh, by the way, why this is also important? Because when we're involving court case, this has to be strictly adhered. Because like I said last time, when there's a prosecution, the lawyers can easily say that, oh, your sample did not follow maximum holding time and therefore they are like invalid. But for information, maximum holding time, if if one chemist did not follow maximum holding time, most likely the level of pollution will be underestimated. That means most likely acquittal. And if it's underestimated, not high enough, most likely the prosecutor will be acquitted because it's not even exceeding the permissible level. Kan? But because of the procedure, the mishandling of sample in terms of procedure, the judge can throw out your case because you don't follow procedure, even though not following the procedure might benefit the accused. But your case also can be thrown out because of the procedural error. Yeah. Okay, so next one is a field quality control and quality assurance. So this one we are going to learn a little bit of quality control and assurance. I think for those who are into the lab, you probably already know what is that. Okay, so let's start off with the problem. Why do we even need that in the first place? Because in terms of sampling, error is around. I'd be lying if I say there is no error coming from myself. If I want to, for a very experienced uh, technician, no matter how experienced they are, when they go to the site and collect water samples, there will be some sort of error, like it's systematic error or random error. Random error is for sure, is that it's just how big. Now, that is because um, contamination or cross contamination will happen all the time. What not? Because the moment you start collecting water sample and you screw capped it, it's already starting changing. You can say contamination in some sort, yeah. Uh, because of this technique, it might cause inaccuracy or the lack of precision in your data. So that is what we're trying to prevent, yeah. Oh, before I continue to the next slide, this sampler is actually holding a grad sampler, weighted bottle sampler attached to a pole. Uh, we have this, yeah, 3 poles in Faculty of Applied Science. I was hoping on Thursday, next Thursday, they're going to show us this one because this one is quite cheap. Hopefully you can see one and you can test one yourself. Yeah. Usually is attached to a rope, but this one perhaps they just want to collect surface water samples, so a pole is enough. Okay, now what is quality control? You can say quality control is there to provide and ensure the quality of the data is secured. Now, this can be said as a procedure. Quality control, you can say, is a procedure that is designed to ensure that as little as possible error is present during the analysis and ensure that your data is as accurate and as precise as possible. So there are sets of practices, good practices inside the lab and also during sampling that is encompassed by this quality control. You can say it's a procedure. Yeah. Now this is a program, a series of this QC program. Oh, by the way, when we talk about QC program, it's not just sampling and analysis. Sometimes it's from the management of data and also the interpretation of data. That also comes under this program. So this entire program is governed by a policy. called a quality assurance program plan. So you can say under quality assurance is quality control, a series of it. Yeah. And usually these are the ones that is in place to ensure quality. So if the lab, for example, most of the commercial lab in Malaysia, including the ones by Jabatan Kimia Malaysia, they look at this very, very importantly, because the reliability of one data very much depends on quality control and quality assurance program. Yeah, so that it is defensible inside the court. Um, and in fact, majority of the commercial lab outside there, either, whether they are certified by ISO or not, also depending on this one. When ISO auditor comes in, they will look at the file. Where is the QA/QC file? Straight away, they will know it. Okay. So implementation aside, of course, they will audit. Implementation aside, the management. This is called one of it. Yeah. So quality samples are a way to evaluate the PARCC parameters. So you might ask, what is that? So these are the PARCC parameters, in which they are precision and accuracy and some others. But I think I don't need to explain to you kind of what is precision and accuracy. I think this one has been learned since secondary school, so that's why I will skip. Yeah. Perhaps you haven't heard about representativeness, completeness, and comparability. Now, these are the parameters that will be in place aside from precision and accuracy to define how reliable is our data. Yeah, coming from the QC procedures. Now, of course, from the QC procedures, in order to maintain these parameters, there are certain ways we can do it. So for today, we're going to look at just the sampling aspect, in order to ensure these parameters are strictly adhered. So PARCC parameters also increase the level of confidence in our data. And if you have a chance to look at the reports, the reports of researchers and also auditors, they will always present their data, and they always tell you what is their confidence level. Yeah, because from there, it gives the impression how reliable the quality of one data. So usually the words that you hear all the time, either 95% confidence or 99%. Very rarely we use 90, although it may be used, but usually it hovers around 95 and 99. Because when we talk about statistics, error that can be negligible, 5%. So 95% confidence yeah, at least. Okay, so representativeness, what is that? Now, if you look at diagram here, the lake water, if I want to collect a lake water that big, and I want to collect this little, does it represent the entire lake water? Very much depends on our technique, betul tak? And also our sampling program. Because if you just want to look at the quality of surface water, then okay lah, you do compositing from one place to one place based on grid sampling. You collect a little bit and you mix it up. That represent the surface water. But does it represent the entire lake? No. So how do we ensure that it represents it? You see, that is a question that a lot of people may not be able to ask, because there's no way you can fully represent this lake water, but we can collect a sample based on the techniques that we learned before, so that it is as near as possible, not exactly, but as near as possible to represent the lake water sample. Okay? And there's one point, representative data should result in a repeatable data. So let's say if you have another round of monitoring, you come back to the same lake and you use the same technique, you should be able to get more or less the same data lah. It is repeatable if the water samples that you collected is indeed representing this lake. Yeah, so that's representativeness. Another one that you need, we need to consider in order to maintain the quality of our data is completeness. So what define completeness is the percent comparison between the amount of data intended to be collected versus actual amount of valid or usable data collected. Now, I'm not going to lie, when you collect water samples, kan, based on the analysis, the data comes back, sometimes it's very, very disappointing, especially when you're looking at analyze at a very low level. When there are more noise than signal, you're actually looking at zigzags, so you don't know where is the analyte. And at times, some of the samples you may need to eliminate or expose because you already know there are errors, like the errors, the mistake when handling the sample. Some of the samples when you handle, they are probably exposed to sunlight or exposed to the higher temperature for a certain time, then it becomes invalid. So what do? You have to eliminate lah kan, because it is no longer valid. So you have to eliminate the samples. So that comes back to the question, if you have a reduction of sample size, that it still represent the sample in terms of completeness, maybe, but not complete. So back to the question, will the data collected be sufficient to give you an accurate result? You see, these are the things that we're trying to prevent, yeah. That is, but there's one thing is in a dilemma. You want to collect as many samples as possible, but then you need to look back at your own budget. You see, that is a dilemma, which is why having a good QC procedure is always a good idea, because you can prevent this from happening, all these errors. So next thing is the key concept of QA and QC completeness. How do you design and how valid is your data? It comes down to the sample size. You cannot collect too many, you cannot collect too few. And when you're collecting, or you also need to look at what are you looking and the limitation. Because why? Sometimes when you collect enough samples that is within your control, you don't need to analyze all that. So you collect a lot of samples, you can keep it. But then you also need to look at the samples. Do they have high enough analyte so that you can analyze it? Because if you have levels at ppb and you have ICP OES, then cannot lah. Now ppb is only measurable by ICP MS. Okay, I'm giving you example. Some instrument, they are very sensitive, some are not. So it's part of the entire thing lah. When you do samples, you also need to match it with the instrument that you're going to use, and also the methods that is applicable in your program. Yeah. So would your data be sufficient if high humidity result in error readings? Now, Malaysia is very famous to have very high humidity, up to 80, 90% at times. Will the humidity affect your sample? Maybe yes, maybe not. Temperature, yes. Humidity, you see, your sample is already liquid, so having more water, will the humidity significantly increase the volume? Well, in Malaysia, maybe not, but in temperate countries where the humidity is low, that is a big factor. Now, for those who have already gone to overseas, when you when you have a glass of water at a very low humidity, after a certain time when you go back, the entire glass is empty. So humidity in Malaysia probably is not really a big problem, but it's a bigger problem in a very dry region. Yeah? Because it reduces volume, and of course it will going to increase the concentration and light possibly. Okay, is the data valid if the readings are outside the measurement range of the instrument? Of course. You have to make sure that the sample that you collected have to be preserved and pre-treated. If it is outside of the measurement range, you have to pre-treat it. Now, for example, if if the analyte has a concentration exceeding the measurement range of the instrument, you have to dilute it. So example, UVVs lah. UVVs is always like that. If you have a chance to use UVVs, you always need to dilute it. Now, another case, very similar to the earlier points that I explained here. If you want to measure the very small concentration of pesticide, volatile some more,
you might need to concentrate it. There's a technique. We can concentrate organic matter, extraction we call it. But again, that is part of the lab pre-treatment, guys. So I don't touch too much lah. Yeah. So when it comes to comparability, now this is one way lah that we want to see how well or how accurate a data is by comparing. Using different instrument or maybe different operators. So I come straight to here lah. I think this one is a very popular or very common instrument lah. Hand carried somewhere, anywhere, can be operated by battery. Now this one is very similar to UVV's spectrophotometer. One is portable, the other one is desktop. But there's one very important thing. UVV's spectrophotometer, usually they are very, very sensitive. So you can say that they can be much accurate than this one. So the data that comes up from these two instruments can be different in terms of their accuracy. And when it comes to accuracy, it's a matter of thousands, sometimes millions when it comes to fines. Because if you measure using this one, again, there is a very high risk that it may not be accurate. And then the defense lawyer can say, your instrument is not accurate lah, boleh percaya ke? And then, okay lah, the judge, if they are convinced, that okay lah, thrown out, acquitted, because your data is not good in quality. Kan? Example lah, yeah. Okay, so when we talk about QC in environment measurement, a lot of things that we need to consider in our instrument lah. How sensitive they are, so how much of small amount they can pick up, the detection limit, how small they can detect also, and also the measurement range. Always make sure they falls into the ability lah. So a sampler like ourselves may not be like want to consider this one, but later you're going to do your assignment. You're going to write an sampling and analysis plan. Now this one is compulsory. There will be a manager, a head, specifically assigned to sit under QA and QC group to monitor all this. So this person will have to be very good lah in chemistry, because from that point onwards, and also the method, then they will going to formulate and work together with all the samplers outside and tell them how exactly they should sample the water. Yeah. Okay, now here are the things that we use to ensure high quality of our water sample. So in quality control procedures, we can divide into into two sections lah. One is the field QC, the other one is the measurement and also lab QC. So lab also they have QC inside the field. When you collect water sample, you also have to adhere to this one. Okay. Now usually it comes in a table lah, a list of things that you need to prepare in order to have a quality control on your sample. Now these are field duplicates. So I'll explain in a minute. What is field duplicates? Split samples, performance evaluation samples, trip, equipment and cool temperature blanks. So blanks, spike samples, duplicate, a lot of these things. Yeah. And on top of that, inside the table also, you might also need to note down what are the frequencies, okay, the frequency of the sampling, the acceptance criteria, the control limits, the corrective actions that will be done when acceptance criteria are exceeded. So these are like the countermeasures. Let's say after you measure all these so-called samples, QC samples, and you discover that they are not within the acceptable region, that means something is wrong. Then what do? You find out what's wrong, and then countermeasures. You see, we don't usually go back to the same site and sample another time, because that probably do not represent the earlier samples that we have collected. But what to do, if something is wrong, then you need to find out what's wrong. But there is a way. If the QC field is done properly, you don't even need to go back to the site and do another round of sampling. You can just quantify the error and do correction if the QC procedure is done correctly, or the QC sample is done correctly. Yeah. So that is a benefit lah. One of the benefit of having a QC in place. Another type of QC is the lab QC, or the field measurement. Now this one usually involve the use of instrument to measure the parameters directly. So if that is the case, kan, uh, you will have all the things that you have, QC samples that you have earlier. Same thing, you have frequency, acceptance criteria, and corrective measures. But this one might involve one more thing. While earlier you don't have instrument, but this one you may have. And having an instrument, it's only natural that you need to have QC in determining its accuracy and precision. So a lot of calibration might be involved. You're going to use a lot of standards to calibrate your instrument. And perhaps not just instrument, maybe operator also. Because different people may have different ability and also knowledge in conducting this procedure, any procedure either in lab or maybe in the field. So human error is a big error also in our sampling. Yeah? So these are the examples that you need to take note and make sure that you know. These are the QC samples that I will explain bit by bit. Trip field blank, equipment or rinsed blank, duplicate, replicate samples, spike samples, split samples, and blind samples. They sound very complicated, but they are very important. So why they are important? Okay, I start off with trip blank. So what is that? It is a sample container that is filled in the laboratory with deionized water. So maybe a container. Before you go for field trip, you fill it first, the container that you're going to use, the same container you're going to use at field. But before you go in the lab, you fill it with deionized water. And then this whole container with deionized water, you bring it to the site, you handle it. You collect your water sample, um, and then you bring it back. So this whole container is filled in the lab, bring it to the site, bring it back without being opened. Okay, you only open when the analysis is conducted. So why is that? Now this is called trip blank, is to determine if there is any possibility that a contamination happens during your when you commute from the lab to the site and from the site back to the lab. So this is to measure if there is any factors that might cause the release of contaminants from the container. Sometimes it's not just from the container, yeah, because inside your distilled water or deionized water, you already have something inside, but due to the conditions like temperature or maybe sunlight, that might change the distilled water or the deionized water. So you see, it measures the conditions. What are the impact of conditions towards the quality of your deionized water? So that is what we call trip blank. Yeah. Now, the other one is called field blank. Okay, don't be confused. This one is more or less the same. The only difference is that this field blank is filled at site. So just now, trip blank is you fill in the lab. But this time, the water is filled when you arrive at the site. Before you start collecting water sample, you open the empty container, fill it with deionized water, close it back, and then you continue with the rest of the sample. So why is this? Now this one is completely different. The reason for determining this field blank is to see if the condition during that time, that includes the influence of air also. Yeah, they want to see what are the conditions in the field that might influence the quality of your distilled water, and hence also your water sample. So they are a little bit different. It looks similar but slightly different. Yeah, but usually we always do field blank lah, because I mean trip blank, they're usually very small, very small. But it does happen lah, especially when you have a different manufacturer in the container. Some manufacturer, they are very good quality, some of them not. If you're in a tight budget, kan, and if you buy a cheaper container, maybe the trip blank lah is what you need to add one more. Yeah. Okay. So what about equipment and rinse it blank? Now, rinse it blank is collected by rinsing the equipment, not just equipment, the container also. And then this rinse is collected. Now, why this is so? Because the equipment and also the container might have prior contamination. I know the good practice is you clean up your equipment before you store it. And before you store, you also need to rinse it. Now, this is how we can get some idea if the source of contamination comes from the equipment itself. Yeah. Now, the equipment you might think is the measuring device card, but some of this equipment, especially in groundwater, they may come from the tube itself. Tube well, they have iron tube. So that might be a source of contamination, and you also may need to quantify it. Yeah. So as usual, you rinse it, treat other samples as well. If you use preservative, then this one also need to be added with preservative, and then you carry on and take it back. So this one measures lah if the error comes from the instrument. Duplicate and replicate. I think this one no need to explain code. I think this one is very common. Why do we need to do this? Is because we take several more samples. I mean, when you collect it, you collect 2 or 3 more. And then after that, what do? You analyze and you take average result and you determine its standard deviation. Now, why this is so? Because we want to know if the data is precise or not. So this one is very important to determine the precision lah. But of course lah, when you have duplicates and replicates, you were going to see how varied is your data. And if you have prior information on when and how you collect, you also can know if those few variations can give you this result. But usually duplicates and replicates, we determine the standard deviation lah, as a way to report precision. Yeah. Okay, split and blind sample. Now, this is a sample that's collected and mixed thoroughly. It is divided into 2 or more subsampling. Now, these subsamples, we are going to send it into different lab or different operators. Now, this is to determine, okay, to determine how precise is the sample. Because like I said, when you send to different lab, they may have different protocols or also procedure to analyze one sample. And these protocols, although it should be similar, but you see, it's governed by human, and human is like uh, prone to errors, right? So instrument also is another factor for error. So based on this, you are going to see if there is a lack of if the error comes from the lack of adherence to protocol, or maybe due to just pure human genuine error. Okay. So this split and blind samples, we keep it just in case lah. If the data we want to know how accurate they are, this one is one. Yeah. And then spike sample also is used to measure accuracy. When a known concentration of analyte is added to the sample, so at field you can add this so-called standard. Now this standard is defined as a chemical that you know exactly the concentration. So you add it into the distilled water, you can expect that concentration to come up. And then after that, once you have collected in the site or maybe from the lab, you bring it back for analysis. So these are the samples that we usually going to see. Like for example, you added 10 ppm of cadmium, for example, and the analysis turns out 9.9 ppm. You can say the rest of your analysis are all accurate. Your sampling is spot on, no problem. So you see how we measure accuracy using this one, spike sample. Yeah. And of course, when we determine this so-called the performance of this spike sample, we usually have a keyword to this one. We call it percent recovery. So that's why when you look at a research paper, they will always see this word percent recovery. So what is recovered? Is the standard. The standard that we get. Let's say you put 10 ppm, you get 9.9 ppm back. That means your recovery is 99%. Very, very high. no question, very accurate. Yeah, your analysis. Okay, so I think we are at the end of our lecture. Still have 15 minutes to go, and I intended to go through very quick of the groundwater sample. So these are the questions that I don't think I have the time to go through. So these are the reminder lah, yeah. What if things happen and what you should do? Now there is no answer to these things, but I strongly encourage you to answer this question and then check yourself online. See whether the things that you should do is exactly what you should do. Yeah. Or else you can have a session. We can have a session elsewhere and we can discuss this over in the forum in new future later. Yeah. Another questions that you can see here are not questions, it's a list lah. What to do and what not to do during the maintenance calibration of instrument, but this one may not be applicable to sampling, so that's why you read it yourself lah. And so yeah, once you have performed all this QC procedure, then you already have how good is that QC procedure, whether they are accurate or not. So in terms of the quality assurance plan, project plan, it is compulsory that you need to review the data in terms of quality, yeah, of your data all the time from time to time so that you can make improvements. So if the data is not good enough, then you have to sit down and see what else can you do? How do you improve the procedure? Either you change to a more accurate instrument, you want to expand the sample size or whatnot, everything is under here. And it can be revised from time to time, yeah? So, okay, uh, these are the things that I've said earlier. QA is higher up than QC. It's policy. It's more of management on how do we ensure the quality of our data. I think I've explained all just now, so I think I'll just move on. And this is supposed to be a pre-lecture movie to show you other way of collecting water sample for drinking water, for wastewater. But these are the ones that I couldn't afford to supply to you because of the time constraint. And I hope you can watch it yourself lah, later on. I'll share the slides with you so you can watch it later. So that is all. Oh my God. Oh my goodness. I only have 10 minutes. Uh, I think I'll take you through lah, yeah. I'll take you through. I'll stop right here. And then I'm opening the groundwater sampling analysis. It's just 12 slides. So I think we should have enough time. And I think for those who have common sense, you should know lah why I insist to show you groundwater. I think you should know kan kenapa. Okay. We need to chase that. Okay, groundwater sampling analysis. For your information, the authorities that govern this groundwater water monitoring, first of all, Jabatan Mineral dan Galian, and then after Jabatan Alam Sekitar, and also part of it, Jabatan Pengaliran dan Saliran. So they have the authority on this. They have overlapping authorities on how to govern this groundwater monitoring. Okay, now, first of all, where is groundwater? Of course, underground. So they have this zone that we call vadose zone and also phreatic zone. Now, where is the water is available? They are under here, the water table. Now, because the soil is a porous substance that water can flow through, but at a certain horizon, a certain level, there will be a semi-impermeable level where either is lined with clay, water cannot pass through easily, or maybe bedrock that is completely solid. So because of that impermeable level, water will accumulate, and that is where you get this groundwater. You can say groundwater is underground river. They will still flow. Yeah. So you have here water table. Once it reaches the water table, that's where you can collect your water. Yeah. So you can say that groundwater is collected in the saturated zone. Why? Saturated with water. And it has to be deep enough. So that is why. Not too many times that you can go and monitor groundwater, because why? This tube well constructed by, if not mistaken, DOE, They construct this tube well to monitor groundwater, and there are not many of them. It depends on the location lah. Yeah. So how is this constructed? This stainless steel tube, they are hammered down into the soil, and then water can be collected up here. Yeah. So the construction of this I won't going to elaborate, but you can collect lah from this tube, and usually by so many means. And the easiest way, the most traditional one, is the baler. Baler is a plastic device. It's just like a camera tube, a camera sampler, only this time they are plastic, and inside here they have like a plampong we call it, yeah, in which once this one is lowered down, water will start comes up, and then once the water is fully filled with this buoy, the water pressure will press this buoy down, and then it will stop water from coming out. So you just pull it up, and then you fill whatever like your sample bottle. So the bottom fill balers, you will have a YouTube video. Once again, you can watch it yourself how this is done. This is quite straightforward. Uh, Usually, I mean, these are the methods lah that people use when you don't have enough money and technology is not really a matter. Yeah. So this one, if you have time, then okay lah. This one is okay. You can use it. But if you have money, yeah, like for example, the operators of landfill, and you want to sample landfill leachate, they will always going to use a pump. Pump is much more simpler lah, because you know what, the tube well, because sometimes they are very deep. You want to put down there, how many times can you afford to like pull and pull down and then pull out? It is very, very tiring. So that's why pump is more preferred lah, more practical actually. Okay, what is done is that now there is a pump attached to a tube. So this tube will be lowered down into the tube well, and they will start pumping water. How this is work is like the peristaltic pump, they have a rotor, they keep on rotating, and because of this shrinking and expanding motion, they will going to make water flow and draws water from deep. Yeah. So this is one. Another type of pump, we call it a bladder pump. Now this bladder pump is what people say is more preferred. I believe this is the one that is more preferred in pumping up water, because they say that they are the one that can cause minimal alteration of sample integrity. I think it's the way they work lah, yeah, how this is done. Um, if not mistaken, they are like water that is like work very much similar to peristaltic pump, but they have a diagram that diaphragm here that they can expand and shrink. So based on this motion of expanding and shrinking, water will comes up. It's very similar to the rotor of the peristatic pump, but this one is expand and shrinking. Okay, you can watch the video how bladder pump works. So this is how it works. But there's one more thing that you have to remember. Every time we need to sample groundwater, we need to make sure that contamination at its lowest level. Now, because why? When a tube well is shut down, bacteria is there, definitely. And usually inside the tube well, there is no flow. It's not like river. It sits there. So you can see that whatever whatever the groundwater that is already inside the tube, they will be different because of the lack of flow, the lack of oxygen, and whatnot. So when bacteria accumulated there, the water parameters is different than the one deeper down. I mean, deeper down in the aquifer, which is why before we collect groundwater sample, we need to first purge. Of course, groundwater flow, you need to measure it. Now, this one you can use uh, a hydrologist to tell you how is the groundwater flow. Of course, you can also measure using the from the tube well as well. But most importantly, in order to eliminate and reduce the error from cross contamination, I mean the water, the groundwater already tapped from the tube must be removed. So how does it work? You need to pump first, remove the as much of volume inside the tube first, so that you can remove not only the entrained water that's trapped inside the tube, you also can flush at the same time. Flush the tube with whatever the contaminants still sticking inside the tube. You see, bacteria, they're very stubborn. They can They can have like, they can form biofilm from anywhere. So the tube, the water tube, they may have it, and flush it is a good idea. Okay. So of course lah, not just the tube, but the pump. You see, the tube, unless you buy it new, now even if you buy it new also, there might be a source of contaminants from a new tube. What about old tube? Now these tubes, they are made of plastic or maybe rubber, and they degrade over time. So when they degrade, they might introduce new contaminants or analytes. So you need to remove first. So it's a good idea lah. When you are flushing and purging the tube well of the stainless steel, you also purging the rubber tube as well. So all tubes needs to be cleaned up before an accurate water sample can be collected. Okay, so these are the things lah. How do we know we need to stop? Now, when a stabilized condition is obtained, so this is the guidelines lah. How do you know the water is stabilized? Is when you have a DO of 0.3, turbidity of 10% and whatnot, everything. This is just a guideline lah. It's never being strictly followed lah. Because why? When you purge, sometimes the groundwater may not follow the same parameter. But how do you know? Is when during purging, you also measure at the same time. They will keep on fluctuating. Yeah, they will keep on changing. So you will only stop when those parameters starting to stabilize. So when they stabilize, they stop changing, then is where you know, okay, you can stop already and start collecting, yeah, your groundwater sample. Okay, so cross contamination may happen, like I said, in the tube and also the equipment itself. So always flush it properly before you collect those samples. And that is all.